Hello, my name is Josef Horák, and I'm the Senior Application Specialist at NenoVision. Welcome to the first webinar in the Coffee Break with NenoVision series. So this one is dealing with NenoVision's unique approach to AFM and SEM data correlation, and of course we'll be glad if you'll stay with us for the rest of the webinars that are streaming always on the same day, only 1 week apart. And the next one is happening on July 2nd and is dedicated to 2D material imaging. Just to remind you that in this streaming format, you can only ask questions using the Q&A chat window. Since the slides are pre-recorded, I can answer your questions during the stream, and if there are going to be any important questions, I will do my best to answer them on microphone by the end of the webinar in the Q&A section. Enjoy the presentation. Welcome to today's presentation focused on novel approach to correlative imaging through CPEM technology, which is one of the key features of NenoVision's atomic force microscope called LightScope. LightScope represents unique atomic force microscope, which is designed to be easily integrated into a variety of scanning electron microscopes. And in the following slides, I will explain all the benefits coming from the atomic force microscope and scanning electron microscope connection, this time with focus on correlative imaging. Why to actually combine AFM and SEM systems? Atomic force microscopes and scanning electron microscopes are two of the most used and in fact complementary techniques for sample analysis in the nanoscale. Nevertheless, since the principle with which they observe and interact with the sample surface is completely different, they provide very different set of information. AFM monitors an interaction between a physical probe and a sample surface, and for that reason represents a tool of choice for topography and roughness measurement with sub-nanometer resolution. AFM also enables analysis of mechanical, electrical, and magnetic properties. On the other hand, scanning electron microscope observes and analyzes the sample surface using a focused beam of electrons. This interaction produces various signals, so besides fast 2D imaging in wide range of resolutions, SEM can provide information on sample composition as well. Further possibilities of SEMs, such as surface modification or nanomanipulation, will depend on their additional accessories. So with that being said, the motivation behind LightScope design is as follows. First, the AFM in SEM systems allows for efficient yet complex in situ sample characterization that combines capabilities of both techniques. And second, it brings completely new possibilities for advanced correlative imaging, which allows analyzing samples in a way that was difficult or even impossible by separate SEM and AFM systems. In general, correlative microscopy or correlative imaging is defined as sample analysis by two or more distinct imaging modalities, and it should provide more scientific insight than would have otherwise been possible using each imaging modality separately. For that reason, this concept is sometimes coined by the 1 + 1 = 3 expression. Traditionally, the correlation is achieved by imaging the sample by several techniques subsequently, followed by data analysis and final image overlay. For instance, RISE, which stands for Correlative Raman Imaging and Scanning Electron Microscopy, belongs to this category. There are also approaches for simultaneous measurements of multiple signals, such as correlative light electron microscopy, shortly CLEM, combining an optical microscope with a SEM into one system. Common issues of the traditional approaches are, first of all, locating the same region of interest on the sample by different techniques can be extremely time-consuming, something which gets increasingly more difficult with micrometer or even nanometer-sized features on your sample, or whenever the imaged feature changes its properties over time or under different imaging conditions. To tackle the above-mentioned issues, it would require high initial investments into sophisticated, dedicated instruments and sample transfers. Other problems with image correlation can be caused by data incompatibility between used devices, such as different data formats, different pixel count or pixel size, etc. LightScope is equipped with correlative probe and electron microscopy technology, shortly CPEM, that enables simultaneous AFM and SEM data acquisition. In the AFM and SEM setting, the SEM's wide range of imaging resolution is very helpful to precisely localize the region of interest on the sample and to precisely navigate the AFM tip, making the whole sample analysis extremely time efficient. Using CPEM, AFM and SEM data are captured under the same conditions in the SEM vacuum chamber, at the same time, in the same place, with the same resolution, using the same data format. Simultaneous acquisition of AFM and SEM data in the same coordinate system enables their precise correlation into one three-dimensional image, which provides more information than each imaging technique separately. And based purely on the imaging capabilities of SEM and AFM systems, the combined AFM and SEM approach really represents all-in-one concept for comprehensive yet time-efficient sample analysis. And the goal at NenoVision is to be able to incorporate all of the SEM and AFM imaging capabilities for complete correlative analysis. As already mentioned, CPEM stands for Correlative Probe and Electron Microscopy and represents the next step in correlative imaging. So let's have a look on how it actually works. On the sample, the electron beam points close to the AFM tip with a constant offset. And during scanning, the AFM tip and electron beam remain static. Sample is being scanned only by the LightScope piezo scanner, which enables simultaneous detection and acquisition of AFM and SEM signals at the same time, in the same place, and under the same conditions. This technology is unique to LightScope and was developed for seamless data correlation. Once the AFM and SEM images are captured, they are subsequently correlated into one image, which we call three-dimensional CPEM view. The information of material contrast in the two-dimensional SEM image is extended into third dimension using the AFM topography. CPEM view can contain multiple channels as shown on this sample of tungsten chromium with hafnium oxide particles. Here, the AFM topography was correlated with the data from secondary electron and backscattered electron detector. Here, the series of videos will show you capture of actual sample measurement that clearly demonstrates the key features of CPEM technology. And for that purpose, I'm going to use shortened measurement of chemically polished strip steel sample. The steel alloy is composed of several phases visible in SEM, whereas the AFM gives us the information about morphology and roughness of the etched surface. And correlation of AFM and SEM provides comprehensive information about the sample surface and the etching rate of different phases. Here we can see SEM overview of the sample and location of the area of interest. As you can see, the AFM probe is positioned roughly in the center of the view. Once the desired spot on the sample is found, it is then very easy to precisely navigate the AFM tip to that area. As the AFM tip comes into contact, we can visualize that by tilting the light scope. We could perform the measurement in tilted position, however, this would be normally used, for instance, for focused ion beam applications. So back to 0 degrees, here you can see positioning of the electron beam right next to the AFM tip. With that, everything is set for simultaneous AFM and SEM data acquisition in the NenoView software. And as you can see in NenoView, during sample scanning, both SEM and AFM channels are being recorded at the same time. Of course, combination of appropriate channels can be chosen for your particular application. And please know that sample scanning was sped up for this demonstration. Once the scan is completed, chosen AFM and SEM channels are subsequently correlated by matching the identical spots. Data from NenoView are compatible with the Gvidion software that we use for data post-processing. Each channel in the saved file represents exactly the same spot on the sample and can be adjusted separately. In the last step, the adjusted images are merged into the three-dimensional CPEM view. In this case, the AFM topography was combined with the SEM data, which here can be either SE or BSE signals. And this was to demonstrate, in short, the CPEM technology in real use. Now let's talk about the main application areas for combined AFM and SEM instruments. Using Lightscope together with SEM to evaluate topography versus material contrast is probably going to be the most used feature of CPEM technology. So let's go back to the tungsten chromium sample with hafnium oxide particles. For instance, the pores with hafnium oxide particles on the SEM image might look identical, but the AFM topography reveals important differences. Some features are elevated, some are depressed. On the other hand, the chromium ridge faces are invisible in the topography, but are clear in the SEM image. And as we have seen already, the CPEM correlated image incorporates all this information for clear data interpretation. And for this application, the other key benefits of CPEM technology and the AFM and SEM approach were fast localization of the region of interest, very fast measurement, and also fast data processing, including image correlation. These are all application examples where correlation of AFM topography with the SEM material contrast was the primary goal, however, usually connected with other properties of the sample, such as characterization of mechanical or electrical properties, which leads us to the next slide. Here, the presented applications will demonstrate further possibilities of CPEM technology, either correlation of less usual datasets or how the proximity of the AFM tip and SEM electron beam can be utilized for advanced applications. So in the first application, the local mechanical properties of graphene membrane were investigated by energy dissipation. Put simply, energy dissipation technique primarily enables to identify softer and harder parts of the sample. And to be able to interpret the data clearly, it was useful to correlate mechanical properties with material contrast provided by SEM in form of BSE signal. The next application shows characterization of various defects in gallium nitride-based semiconductor. Here, the CPEM technology enabled analysis of identical region of the sample by three techniques. The AFM Lightscope reads the probe height information and combines it with the secondary electron intensity signal from the SEM and electron beam-induced current signal. These recorded values provided three maps that allowed correlation of topography changes with the electrically active surface around them, which is the negative electron beam-induced current contrast, and also with SEM-SE intensity. The last application shows a concept which demonstrates possibilities of having the AFM tip close to the SEM electron beam. The imaging mode, called conductive CPEM, is an extended version of the standard conductive AFM, but unlike conductive AFM, enables conductivity measurement even in insulated areas of the sample. The sample, which is gold on silicon, contains areas that are conductive, non-conductive, but also areas that are conductive but insulated. The standard conductive AFM fails to image the insulated islands, and they appear black. The unique conductive CPEM will image even the insulated areas Since the electron beam of SEM serves as an external source of electrons and replaces the need of an applied bias, but the bias between the AFM tip and the sample can still be simultaneously applied. In our previous webinar, we have shown the overview with focus on more general advantages of LightScope and the AFM in SEM approach. Here I'm going to summarize only the key points related to NenoVision's unique CPEM technology. So the most important feature of CPEM is that it enables simultaneous acquisition of AFM and SEM data at the same time, in the same place, and under the same condition. And for that reason, the resulting correlated images are perfect. And as we've seen in the presentation, even though correlation of AFM topography and SEM material contrast is going to be probably the most used feature, CPEM can accommodate various channels both from the SEM and AFM. So far, CPEM supports correlation of SEM's SE, BSE, and electron beam-induced current signals together with AFM's topography, mechanical, and electrical properties. NenoVision is working hard to be able to incorporate in other datasets both from the SEM and AFM systems. Those should include, for instance, data from EDX and EBSD detectors or magnetic force microscopy. Lastly, the conductive CPEM clearly showed a measurement mode, which takes full advantage of the AFM tip and electron beam proximity, and it's obvious that there are way more applications where this setting will enable many more unique and unforeseen measurements. Dear all, I hope you have enjoyed the webinar and thank you for your attention. So now we are starting the Q&A section. So I hope that we have answered as many questions as possible in the chat window. But anyway, we have chosen 3 questions that are important, and we think it's better to answer them on the microphone. So the first question is, you have shown many accessories of SEM, and can you correlate all of them? And if not, which ones? So as was stated in the presentation, so currently we are able to simultaneously acquire and correlate AFM images with several SEM signals, such as SE, BSE, and electron beam induced current signals. And of course, at NenoVision, we are working hard to incorporate as many of the accessories of SEM and also the methods of AFM together. So for instance, the other mostly spectroscopy modes like EDS can be currently nicely measured in situ, but for now, they cannot be acquired using the CPEM. The next question is, what is the minimal or typical distance between the AFM tip and the E-beam spot? So the offset between the AFM tip and the E-beam is usually set a few percent of the overall image, 1 to 5%. So for instance, if your scan range is 10 micrometers, the offset distance in that range would be 200 to 300 nanometers. The minimal offset might depend on the measuring mode, the E-beam current, and so on and so on. But in general, successfully tested offset distance would be about 100 nanometers. Anyway, the offset value is not related to the correlation precision. It only defines the area which is cropped in the CPEM image. Okay, and the third question is, does the E-beam influence the AFM tip? So in general, yes, it does. And this is the reason why we specify the certain offset to eliminate the E-beam influence on that tip. So as mentioned, 100 nanometers distance was tested and provided very nice results. But clearly it will vary according to your application. So on the other hand, you can utilize the E-beam or the AFM tip interaction in specific measurements. And these are novel imaging techniques. And I think that those should be discussed individually since this is a quite complex topic. So with that, I hope that all questions were answered, and I would close this section. And if you will have more questions, please visit our webpage, which is nenovision.com, or you can also email us directly. And once again, I would like to invite you to the rest of our webinar series that are called Coffee Breaks with NenoVision. And the next one will be streaming on next Thursday, which is July 2nd, and is dedicated to imaging of 2D materials. And with that, we are coming to the end. And on behalf of the whole company, we thank you again for your attention. And we would like to see you at next webinar. Bye.